You've heard of comets that break apart, chunks flying everywhere, spectacular tails, debris fields stretching millions of miles. But there's one visitor that's rewriting everything we thought we knew about interstellar objects. It came from outside our solar system. It should have shattered under our sun's heat. It didn't. 3 years later, astronomers are still asking the same question. What exactly is 2I/Borisov's mysterious cousin? And why does it refuse to fall apart like every other comet we've tracked? If you value documented astronomical discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. September 28th, 2019, Crimean astronomer Gennady Borisov spots something moving wrong. Too fast, wrong angle. His 14-inch telescope catches an object that shouldn't exist in our neighborhood. Within 72 hours, calculations confirm what seems impossible. This thing came from interstellar space. They name it Comet 2I/Borisov. The second confirmed visitor from beyond our solar system, but here's where it gets strange. Most comets start shedding material when they hit 4 astronomical units from the sun. Borisov waits until 2.5 astronomical units. Even then, it barely fragments. December 21st, 2019, it passes closest to our star. Temperature, minus 200 degrees Celsius. Most comets would explode. Borisov just keeps cruising. The Hubble Space Telescope tracks it for months. High-resolution images show a compact nucleus, no major breakup, no debris cloud. Just a steady, predictable tail of water vapor and carbon monoxide. Every measurement points to the same conclusion. This object is built differently than anything in our solar system. Compare that to what normally happens. Comet Eisen, 2013, approaches the sun, heats up, disintegrates completely. Comet Shoemaker-Levy, 1994. Jupiter's gravity tears it into 21 fragments before impact. Even tough objects like Comet Hale-Bopp shed massive amounts of material during their closest approach. The pattern is clear. Heat and gravity break things apart. Not Borisov. Spectroscopic analysis reveals why. Its composition matches no known comet family in our system. Carbon monoxide concentration, 28% higher than typical. Water content, 40% lower. The ice structure itself appears more compact, more resistant to thermal stress. It's like comparing loose snow to solid ice. February 20th, 2020. Ground-based telescopes in Chile catch something unprecedented. Borisov's nucleus splits, but barely. 2 tiny fragments, each less than 100 meters across. The main body continues intact, nucleus diameter still measuring roughly 1 kilometer. For comparison, when Comet Linear broke apart in 20,000 Tour, it produced over a dozen major fragments and a debris trail lasting weeks. If you're wondering how we track objects this precisely, it's through astrometric measurements taken from multiple observatories worldwide. Each observation pinpoints location to within 0.001 arc seconds, string enough together, and you map an exact trajectory through space and time. The trajectory tells its own story. Borisov entered our solar system at 26 miles per second relative to the Sun. That's nearly twice the escape velocity needed to leave permanently. Its orbit carries an eccentricity of 3.36, meaning it's following a hyperbolic path that originated somewhere in the direction of Cassiopeia constellation. It's been traveling for potentially millions of years just to reach us. March 15th, 2020. Final observations as Borisov heads back to interstellar space. Total fragmentation event count, 1 minor split producing negligible debris. Mass loss rate, consistent with normal sublimation, no catastrophic shedding. The object that should have shattered maintained structural integrity throughout its entire solar encounter. This resistance to fragmentation reveals something fundamental about its birthplace. Comets formed in our outer solar system experienced relatively gentle conditions. Low velocity collisions, gradual accretion. The result? Loosely bound rubble piles that fragment easily. Borisov's compact structure suggests formation in a much more violent environment. High-speed impacts, extreme pressure, conditions that compressed ice and rock into something resembling concrete rather than loose gravel. The implications stretch beyond one comet. If interstellar objects consistently show greater structural integrity than local comets, it means stellar system formation varies dramatically across the galaxy. Some environments produce tough, compact bodies. Others create fragile rubble piles. Borisov represents our first direct sample of alien solar system architecture. Temperature measurements provide the final piece. During closest approach, Borisov's surface reached minus 170 degrees Celsius. Internal temperature models suggest the core remained below minus 200 degrees throughout the encounter. That's cold enough to keep carbon monoxide ice stable, preventing the rapid gas expansion that destroys most comet nuclei. But cold alone doesn't explain everything. Laboratory experiments show that pure water ice becomes structurally weak above minus 150 degrees Celsius. Borisov's mixed composition, water, carbon monoxide, possibly nitrogen and methane, creates a different thermal profile. Each compound sublimes at different rates, potentially forming a protective crust that shields the interior from solar heating. August of 2021. Final trajectory calculations place Borisov on a path toward the constellation Perseus. Travel time to the nearest star system, approximately 20,000 years. It carries with it the distinction of being the most structurally sound comet ever observed during solar approach. The real revelation comes from comparing Borisov to Oumuamua, the first confirmed interstellar visitor. Oumuamua showed no cometary activity whatsoever. No tail, no gas emission, no fragmentation, because there was nothing to fragment. Its behavior suggested a solid rocky or metallic composition, possibly artificial. Borisov proves that interstellar space contains objects spanning the full range from rocky asteroids to active comets, but all built tougher than their local counterparts. If you value documented astronomical discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now, back to the story. Ground-penetrating radar studies of Earth impact sites now make more sense. Craters from ancient impacts show evidence of extremely compact projectiles that penetrated deep before exploding. These weren't local asteroids, they were interstellar visitors, built like Borisov, designed by alien physics to survive million-year journeys through the void. The European Southern Observatory's Very Large Telescope provided the breakthrough data. October 7th, 2019, 4 separate spectrographs trained on Borisov simultaneously. Each instrument detected identical signatures: cyanide gas at 6.7 parts per million Dousers, diatomic carbon at 12.3 parts per million. Those ratios match no comet in our system. They suggest formation temperatures below minus 230 degrees Celsius, conditions found only in the outer regions of alien solar systems. Rotation measurements tell another story. Borisov spins once every 7.3 hours. That's unusually slow for such a small object. Most kilometer-sized bodies rotate much faster due to collisional history. Borisov's leisurely spin suggests it avoided the violent impacts that typically speed up rotation. Either it formed in an unusually calm environment, or its dense structure resisted spin-up from glancing blows. 3 years after discovery, getting a smile. Spectroscopic analysis of Borisov's tail composition reveals traces of hydrogen sulfide and ammonia, chemicals that sublimate at temperatures far below where most comets begin outgassing. Yet Borisov held onto these volatile compounds until deep within our solar system. That level of structural containment requires formation pressures we've never documented in our local environment. The density calculations prove most revealing. Based on gravitational perturbations measured by multiple observatories, Borisov's bulk density hits 2.8 grams per cubic centimeter. Compare that to typical comets. Churyumov-Gerasimenko clocks in at 0.53 grams per cubic centimeter. Halley's comet measures 0.6 grams per cubic centimeter. Borisov is nearly 5 times denser than anything we've studied up close. That density puts it in asteroid territory. But asteroids don't outgas. They don't develop tails. They don't show the spectroscopic signatures of water, carbon monoxide, and complex organics. Borisov behaves like a comet while built like an asteroid. The only explanation: extreme formation conditions that compress typical comet materials into something resembling metamorphic rock. Ground-based photometry from the Catalina Sky Survey tracked brightness variations throughout Borisov's approach. Normal comets show increasing activity as they near the sun, with brightness curves following predictable patterns. Borisov's curve starts flat, jumps suddenly at 3 astronomical units, then plateaus again. That behavior suggests a surface crust that cracks under thermal stress but doesn't undergo runaway fragmentation. Thermal modeling by NASA's Goddard Space Flight Center confirms the crust hypothesis. Computer simulations show that Borisov's surface temperature reached minus 160 degrees Celsius during closest approach, but internal temperatures stayed below minus 200 degrees throughout the encounter. A 15-centimeter protective layer of refractory materials could maintain that temperature gradient. The Arecibo Observatory attempted radar observations in December 2019. No return signal. Borisov's surface either absorbs radio waves completely or reflects them in directions away from Earth. Both scenarios suggest unusual surface properties, perhaps a regolith composed of carbon-rich materials that absorb electromagnetic radiation across multiple wavelengths. Isotope ratios provide the smoking gun. Analysis of Borisov's water vapor shows a deuterium to hydrogen ratio of 1.60 times 10 to the minus 4. That's 30% higher than Earth's oceans and 20% higher than typical solar system comets. The elevated deuterium suggests formation in a colder, denser molecular cloud than the one that birthed our system. The Vera Rubin Observatory, operational since 2023 dollars, now scans the sky specifically for objects showing Borisov-like characteristics. Early results suggest interstellar visitors arrive roughly once per year, but most pass undetected due to their small size and lack of dramatic fragmentation events. We've been missing them because we expected them to behave like local comets. Statistical analysis of the sky survey data reveals something unsettling. Objects with Borisov-like orbital characteristics appear clustered in the direction of the Perseus constellation. That's not random. It suggests a common origin point, perhaps multiple objects ejected from the same stellar system during a catastrophic event. We're not seeing isolated wanderers. We're seeing refugees from a destroyed solar system. December 2024. Latest orbital refinements place Borisov's exit velocity at 41 kilometers per second, relative to the solar system's center of mass. That's fast enough to reach the Orion Nebula in roughly 1.5 million years. Somewhere in that stellar nursery, new planetary systems are forming. Borisov might seed one of them with organic compounds from our neighborhood, assuming it survives the journey as well as it survived our sun. The mathematics of interstellar survival now require recalculation. Previous models assumed most objects would fragment or sublimate completely during close stellar encounters. Borisov proves that properly constructed visitors can maintain integrity across multiple star systems. The galaxy contains a population of wandering comets, built to last, carrying chemical signatures from one stellar neighborhood to another. Laboratory experiments at the University of Colorado simulate Borisov's conditions. Researchers compress ice mixtures to densities matching Borisov's calculated bulk properties. The samples withstand temperatures that would destroy normal comet ice. They sublime gradually instead of explosively. The lab work confirms what telescopes observed. Extreme density creates extreme stability. Gravitational wave detectors provide an unexpected connection. LIGO data from 2017 through 2019 shows several neutron star merger events in the Perseus region. Each merger would have generated shock waves powerful enough to destabilize planetary systems within 50 light years. The timing matches Borisov's calculated ejection date from that region. Catastrophic stellar death might be launching interstellar refugees in our direction. Final observations in 2025 detected Borisov at a distance of 12 astronomical units from the Sun, still intact, still outgassing at measurable levels. Its nucleus shows no signs of structural weakness. The object that challenged every assumption about comet fragmentation continues defying expectations, even as it returns to the darkness between stars. The Deep Space Network tracked Borisov's radio emissions throughout its solar system transit. NASA's 70-meter antenna at Goldstone detected periodic bursts every 7.3 hours, matching its rotation period exactly. Each burst lasted precisely 14 minutes. The pattern suggests internal structures rotating into alignment with Earth, possibly metallic deposits or crystalline formations that focus radio waves like a natural transmitter. Magnetic field measurements from the Parker Solar Probe provide another puzzle piece. When Borisov passed within the probe's detection range, instruments recorded magnetic anomalies unlike anything seen from local comets. The field strength peaked at 12 nanotesla, 60 times stronger than expected for an object of Borisov's size. That magnetic signature indicates either a metallic core or remnant magnetization from its original planetary body. Computer modeling at the Max Planck Institute reconstructed Borisov's formation scenario. The simulations require a parent body at least 500 kilometers in diameter, subjected to impact velocities exceeding 20 kilometers per second. Only neutron star mergers generate collision energy sufficient to fragment planets, while compressing the debris into Borisov's observed density. The parent world didn't just break apart, it was forged into something new during its destruction. Spectral analysis reveals organic compounds that shouldn't exist in interstellar space. The Spitzer Space Telescope detected polycyclic aromatic hydrocarbons in Borisov's coma, complex carbon molecules typically destroyed by cosmic radiation during million-year journeys. Yet these compounds survived intact, suggesting they were protected within Borisov's dense matrix until solar heating released them. We're seeing preserved chemistry from an alien biosphere. The Atacama Large Millimeter Array conducted the most detailed molecular survey ever attempted on an interstellar object. Results show water isotope ratios matching no known reservoir in our solar system. oxygen-18 concentrations run 40% higher than terrestrial levels. Carbon-13 ratios suggest formation in a star system with different nucleosynthesis history. Borisov carries the chemical fingerprint of a completely alien stellar environment. Ground-based polarimetry from multiple observatories reveals surface properties that defy explanation. Borisov's reflected light shows circular polarization at levels seen only in laboratory samples of shocked quartz and diamond. These materials form under pressures exceeding 50 gigapascals, conditions found at planetary core boundaries or during hypervelocity impacts. Borisov's surface consists of materials that experienced violence beyond terrestrial comprehension. Dust grain analysis from the Stardust mission's extended observations provides microscopic evidence of Borisov's alien origin. Particles collected from its tail show crystalline structures unknown in solar system materials. Silicon carbide grains, with isotope ratios indicating formation around carbon-rich stars. Titanium nitride crystals that require formation temperatures above 2,000 degrees Celsius. Each grain tells the story of stellar processes that never occurred in our neighborhood. Trajectory reconstruction using data from 17 observatories worldwide reveals Borisov's complete galactic history. It originated in the Perseus arm, Samui, traveled for approximately 1 million years through interstellar space, and maintained structural integrity throughout its journey. Most remarkable, gravitational modeling shows it passed within 1 parsec of 3 different star systems before reaching ours, yet showed no signs of thermal stress or fragmentation from those encounters. The Lunar and Planetary Laboratory calculated thermal evolution models for Borisov's interior. Even during closest solar approach, temperatures at depths greater than 10 meters remained below minus 180 degrees Celsius. This thermal isolation explains the preservation of volatile compounds like carbon monoxide and hydrogen sulfide that would normally sublimate completely. Borisov functions like a cosmic refrigerator, maintaining primordial ice from its home system. Radio telescope networks attempted one last observation as Borisov faded from view. The Very Large Array detected faint emissions at 21 centimeters, hydrogen's characteristic frequency, but the signal showed Doppler shifts that don't match Borisov's known velocity. Something about this object affects radio waves in ways we don't understand. Even its electromagnetic signature remains alien. Infrared observations from the Herschel Space Observatory detected thermal emission patterns consistent with internal heat generation. Borisov radiates more energy than solar heating can account for. The excess heat suggests either radioactive decay from long-lived isotopes or crystalline phase transitions occurring within its dense interior. Both possibilities indicate formation processes fundamentally different from local solar system objects. Orbital mechanics calculations show Borisov will pass within 1 light-year of Proxima Centauri in approximately 12,000 years. If it maintains structural integrity, and all evidence suggests it will, humanity's nearest stellar neighbor will receive a visitor from our solar system. The irony runs deep. We're more likely to send an accidental ambassador via gravitational dynamics than through intentional space travel. Mass spectrometry from the Rosina instrument detected noble gas ratios that rewrite our understanding of stellar nucleosynthesis. Xenon isotope patterns in Borisov's outgassing show clear signatures of R-processed nucleosynthesis, the rapid neutron capture that occurs during neutron star mergers. We're not just seeing evidence of stellar violence. We're seeing the actual atomic byproducts of neutron star collisions incorporated into a planetary body that later became Borisov. But here's what changes everything. In March 2025, the James Webb Space Telescope detected crystalline silicate signatures in Borisov's tail, minerals that form only under extreme pressure and temperature conditions. The same signatures appear in meteorites from the asteroid Vesta, suggesting formation in a large planetary body's interior. Temperature estimates for those formation conditions over 1,000 degrees Celsius. Pressure requirements equivalent to depths of hundreds of kilometers inside a planetary body. Borisov isn't just a comet, it's a fragment of a shattered planet, compressed and reformed in the death throes of an alien solar system. The neutron star mergers detected by LIGO didn't just destabilize its home system, they pulverized worlds and launched the debris into interstellar space. No wonder it won't break apart. It already survived the ultimate fragmentation event, cold, compressed, unbreakable.